Hello everyone, this is Puya. Today I'm going to talk about 5 different sorting methods that we have seen in this course. We're going to see the concept of these sorting methods, and later on I'll show you the implementation. So the first method that I want to show you is bubble sort. So the name comes from this concept that once you have a pot of, let's say, water, and then once you have, like, my drawing is not very good, but let's say you have heat here, and then once you get to the boiling point, the bubbles of water start being created here, and the one that has the highest energy would go to the top first, and then the next one goes, and the next one goes, and the next one goes. So this is where the name comes from. So how bubble sort works is basically you always compare two adjacent elements, neighboring elements. I hope that you can see the numbers on these cups that I have here. So here we have an unsorted array of numbers. So in bubble sort, what we do is just compare two adjacent elements, and let's say that we want to have the smallest number here, the largest number here. So of course the computer cannot see, we can see the whole thing, but a compiler or a computer program cannot see the whole array. It would just see two elements and compare these two, and if there is need for swapping, it would swap them. Right here 10 is bigger than 7, so it would swap them. Then 10 and 8, swap. 10 and 9, swap. 10 and 1, swap. 10 and 6, swap. 10 and 2, swap. Okay, so this is one round of bubble sort. What happens at the end of this round is that we end up having the largest number at the end of the array. It can be a vector, right? So then we have the next round, but this time we go all the way up to here, right? So we don't need to go all the way up to the end of the array. We only need to go up to this element. So again, we compare 7 and 8. There's no swapping needed. 8 and 9, no swapping needed. 1 and 9, swap. 9 and 6, swap. 9 and 2, swap. And the second largest number at the end of the second round would be at the right place. So again, the next round we go up to here. 7 and 8, no swapping. 8 and 1, no, swapping. 8 and 6, swap. 6 and 2, swap. And this is what we have. So again, for the next round, we only need to go up to here. Let me make sure that you can see the whole thing. Yes. So 7 and 1, swap. 7 and 6, swap. 7 and 2, swap. The next round we go up to this point, right? So this is unsorted, this is sorted. 1 and 6, no swapping needed. 2 and 6, swap. Okay, the bubble sort doesn't stop, because at this point we are sure that this part of the array is sorted. So what happens here now, we have two elements, we compare them, 1 and 2, no swap needed, so the whole array is sorted now. This is how bubble sort works. Okay, so you just compare two adjacent elements, and the big O notation of bubble sort is big O n squared. You have n minus 1 steps, and then at each step you just basically have to go through the whole array, not the whole array, but just n minus 1 minus I, which is I is the step number. And then you just have to compare elements and swap them. If you just see that, you would see that in the first time we needed to do n-1 swaps, then n-1 comparisons, n-2, n-3, all the way to 1 comparisons. And if you add them up, you would see that this is gonna be n times n-1 divided by 2. So the big O notation of this is big O n squared. This is how many comparisons we need to have. One of the problems with bubble sort is that if we use the original bubble sort, even if the array is sorted, right, our method doesn't know that. So like what it do, it compares 1 and 2, no swap, 2 and 6, no swap, 6 and 7, 7 and 8, 8 and 9, 9 and 10. So now we are sure that this is the largest number. But the algorithm doesn't stop. It would just keep doing the comparison for this one. 1 and 2, 2 and 6, 6 and 7, 7 and 8, 8 and 9. This is sorted. 1 and 2, 2 and 6, 6 and 7, 7 and 8. This is sorted. 1 and 2, 2 and 6, 6 and 7. This is sorted. 1 and 2, 2 and 6. This is sorted. 1 and 2. This is sorted. So this is one of the problems with the bubble sort, that even if the array is sorted, it's going to take the same number of steps. So one way to modify bubble sort is to have a variable that counts how many swapping we do in each step. At each step, so like here, let's say, like, let me make this one a little bit like this. Or let's just like make the, like, let's 10 go here, and 9 here, 1 here, or actually like this, like this. So like I modified the array a little bit. 10 and 1 swap, 10 and 2 swap, 2 and 6 and 10 swap, 7 and 10 swap, 10 and 8 swap, 10 and 9 swap. Okay, we get to this point. Now we are sure that this is the largest number. 10 is the largest number. We go to the second round, right? But we increment the swap variable. So let's say that we have a swap variable that at the beginning of each round, we make this 0. So 1 and 2, no swap. 2 and 6, no swap. 6 and 7, no swap. 7 and 8, no swap. 8 and 9, no swap. So if you don't have any swapping in each round, it means that your array is already sorted, so you can stop. So this is basically how the modified bubble sort works. You just like, again, like if the array is sorted, let me just like sort this array using bubbles, using modified bubble sort. So initialize at the beginning of each round, I initialize the swap to 0. 1 and 2, no swap. 2 and 6, no swap. 6 and 7, no swap. 7 and 8, no swap. 8 and 9, no swap. 9 and 10, no swap. So it means that the array is sorted. So I don't need to do n2 minus n divided by 2 comparison. I only do one round, n minus 1 comparison. So this is bubble, so modified bubble sort. Now, the next sorting method that I want to show you, which is also, it's going to be order of n squared. It's going to be selection sort. Let me make this like a little bit like this. Just like also like move 1 here, 9 here. Okay, so this is the array that we have. So in the selection sort, what we do in each round, we have, let me grab another marker. Let's say like we have a minimum variable. Okay, so what I do, I select this number to be minimum. And I start comparing. Is this one smaller than minimum? Yes, it is. So minimum becomes 8. And I also like keep the index of this. So like I should actually write down the index 0, 1, 2, 3, 4, 5, 6. So let me call this one minimum index. So initially minimum index is 0. We assume that we select this one to be the minimum, right? And then I compare a min index and ai, right? So does this one smaller? Yes, it is. So I change the minimum index to 1. Is this minimum number? So minimum number is now 8. Is 8 smaller than 10? Yes, it is. Is 8 smaller than 2? No, it is not. So I change the index, minimum index to 3, and now my minimum number is 2. Is 1 smaller than this? Yes, it is. So I need to change the minimum index. Minimum index becomes 4. And my minimum number is 1. Right? I compare 1 and 7, no change. 1 and 6, no change. So now I found my minimum number. What I do, I swap these two elements. Okay, so at each round I find the smallest number, right? So you see that in bubble sort we do a lot of swapping, but in each round of selection sort we only do one swap. The next time I select this index, which is 1, to be the minimum index. And my minimum number is 8. Okay, I compare 8 and 10, no changes. 8 and 2, I need to change. So my minimum index becomes 3, and the smallest number is 2. 2 and 9, no changes. 2 and 7, no changes. 2 and 6, no changes, right? So I went to the all the way from this point to the end of the array. I found the smallest number. What should I do? I'm gonna swap these two numbers, right? So now this part of the array is sorted. This part is not sorted. So what do I do at the beginning of the next round? I select this one to be the minimum index. My minimum number is 10. I compare 10 and 8. This is smaller, so the minimum index becomes 3. I compare 8 and 9. This is smaller. 8 and 7. 7 is smaller, so the minimum index becomes 5. And 7 and 6. Still 6 is smaller, so 6 is gonna be the minimum number, and the minimum index is 6. I swap AI and a min index. So these two are gonna be swapped. Okay, this part of the array is sorted, this part is not sorted. So what do I do in the next round? Minimum index is gonna be 3. The smallest number is now 8. We select this one to be the smallest number. We compare the minimum that we selected with the rest of the array from this point to this point. So 8 and 9, no changes. 8 and 7, I need to change the min index. The minimum number is 7, and the index would become 5. 7 and 10, no changes. So what do I do? Swap these two. This part is sorted, this part is not sorted. In the next round, minimum index, I'm gonna start from here. Minimum index becomes 4. The smallest number I have, the minimum number I have is 9. I compare 9 and 8. So 8 is smaller, so minimum index becomes 5. I compare 8 and 10, no changes. So what do I need to do? I'm just gonna swap a min index and a I. Like I is is associated with the step, with the round that we are at. So we're gonna swap these two, and finally we have two numbers, right? So minimum index is gonna be 5. The smallest number is 9. I compare 9 and 10, right? So no changes happen, so like there is no swapping needed, and we are done. The whole array is sorted. So this is basically what selection sort is. It's slightly faster than bubble sort because we don't do as many swaps in selection sort as we do in bubble sort. Okay. The next sorting method I want to show you is gonna be insertions. Selection sort is also of the big O notation n squared. The next method is insertion sort. So let me actually... So insertion sort is very similar to the way that we play cards, and we want to sort our cards. So let's say that I have this thing and I want to sort them in the order. Let's say like the suits doesn't matter. So if I want to sort them, so I assume that this is already sorted, and then I'm just going to go through this and then move this one here. And then I assume that this part is sorted, this part is unsorted. So then I'm just going to try to make this one bigger and bigger. So this is going to go here. So this part is sorted now. Then I'm going to compare where should I do, like what's the next number to add here. This is the 1, 9, and then the next number here, 10. And this is like how the whole card, like the whole deck becomes sorted. So what we do in the insertion sort, we assume that, let's say like this part of the array is sorted, this part is unsorted. Okay, so now we want to add elements. Actually, I did this wrong. Sorry, I did the insertion sort wrong here. I'm gonna do this one more time. Sorry about that. So sorry. So like we assume that this is sorted. Now we want to add king to it. It goes up here. Then we want to add 9 here. It goes all the way here. We want to add 2 here. It goes all the way here. So we want to add like element one by one. 10, it goes here. Ace goes here. Sorry about that. I made a mistake in the beginning when I was using cards. But here, this is how insertion sort works. Like we assume that this part of the array is sorted, and we want to make this part bigger and bigger. This is unsorted, this is sorted. So if I want to add 7 here, what should I do? What should I do? Let's assume that I'll take this one out, right? And I say that, okay, this one needs to go before this. So I'm going to shift this one here, and I'm going to put 7 here. So now here we have like a sorted sub array. This part is unsorted. So again, what I do, I want to add this one to this sorted sub array. Let's say that I take this one out, right? Compare 10 and 9, this is already bigger than that, so I don't need to do anything. This goes back to where it was. Now this sub array is sorted. This sub array is not sorted. Okay, the next element that we want to add to the sorted sub array is 2. So I'll take this one out. I compare 2 and 10, right? 10 is bigger, so I'm gonna move this one to the right. 9 and 2, 9 is bigger. I'm gonna move this one to the right. 7 and 2, 7 is bigger. 7 goes here. There's an empty spot here, so I'm gonna insert 2 here. So now this sub array is sorted. This one is not sorted. The next element that we want to add to the sorted sub array is 8. Let's say like I'll take this one out. I compare 8 and 10. 10 is bigger, so I'm going to shift this. 8 and 9. 9 is bigger. I'm going to shift this. 8 and 7. 8 is bigger. So that's it. This is the spot for the 8 to go to. Okay, so now this part of this sub-array is sorted, this is not sorted. The next element that we want to add is 1. I take this one out. 1 and 10, 10 is bigger, shift it. 1 and 9, 9 is bigger. 1 and 8, 1 and 7, 1 and 2. 1 goes here, right? So this is sorted. This is not included in the sorted. So the next thing I have to do, compare 6 and the elements of the array. 6 and 10, 10 is bigger, shift. 6 and 9, 9 is bigger, shift. 6 and 8, 8 is bigger, shift. 6 and 7, shift. 6 and 2, this is bigger than 2, so it means that this has to go here. I have to insert it in the right place. So this is how insertion sort works. So again, I'm gonna use the cards so that like you don't get confused. I'm just gonna add more numbers here. Let's say like we added 2 and 3. So here, this is like what I have. Let me shuffle this a little bit. So we start, let me just like take 1 here. So we start from here. We assume that this is sorted. We want to add to the sorted part. So 2 and king, 2 should go before the king. 10 and king, and 10 and 2. 10 is smaller than king, but it's bigger than 2, so it goes here. 3 is smaller than king. 3 is also smaller than 10, but it's bigger than 2, so it goes here. 7, smaller than king, smaller than 10, but bigger than 3, so it goes here. And 9, smaller than king, smaller than 10, but bigger than 7, it goes here. Smaller than king, smaller than 10, smaller than 9, smaller than 7, smaller than 3. It's not smaller than 2, so it doesn't matter like if it goes before or after, it goes right here. And finally, ace and king, ace and 10, ace and 9, like this is number 1. Let's assume that this is number 1. Ace, 1 and king, 1 and 10, 1 and 9, 1 and 7, 1 and 3, 1 and 2, 1 and 2. This goes all the way here. So this is how insertion sort works. So these algorithms can also be implemented recursively. I show you in the slides how they can be implemented recursively, but the recursive version, it's not necessarily more efficient. It's actually like it's gonna take more time because these methods are not inherently recursive. Okay. Now, the next algorithm I want to show you is merge sort. Okay, so merge sort is a recursive algorithm. Let me again make this one a little bit. Like this. Let's say that this is the array that we have. Okay, so in the merge sort, this is inherently a recursive algorithm. Merge sort is comprised of 2 functions. One function that would do the recursive call, merge, let me call it sort. And the other one that merges 2 sorted arrays into a bigger array. So what we do in the merge sort, first what we do is basically we divide the array into 2 parts. Okay, so here we find the midpoint. 0 plus 6 divided by 2 is 3. So let's say that this is the half. This is the first half. This is the second half. Okay, so we say that in order to sort the whole array, let's first sort the first half, then sort the second half, and then merge them together. Okay, so we're gonna sort this one first, then sort this one, then merge them together. Okay, so now we have to sort this array. from index 0, this sub-array. We have to sort this from index 0 to index 3. So again, what we do, we divide this into 2 sub-arrays. Let me put this one here. So I say that in order to sort this one, let's sort this sub-array first, then sort this one, then merge them together. So now I have to sort this one. 6 and 10, again, let's assume that I don't know how to sort this. So again, I'm gonna divide this into 2 sub-arrays. I'm gonna say that, okay, if I wanna sort this sub-array, let's sort this one first, then this one, then merge them together. Okay, so now once you get to one element, then the array is already sorted, the sub-array is already sorted, right? So it's the merging part. So what we do in the merging part, I already showed you like the implementation of the merge function. So what we basically do, we compare the elements of this sub-array and this sub-array, whichever is the smaller, we move it here, right? And then this one goes here, and then we move them back here. So this sub-array is now sorted. Now we can sort this sub-array, right? So now that we want to sort this sub-array, again, like we're going to divide it into 2, right? Like sort this one first, then sort this one, then merge them together, right? This is already sorted, this is already sorted. So we're going to compare the elements, right? 8 is smaller than 9, sorry. 8 is smaller than 9, 8 goes here, and then 9 goes here, right? And then they move back here, okay? So this is what happens. So now this sub-array is sorted, this sub-array is also sorted. Now I want to merge them together. I compare 6 and 8, 6 goes here. I compare 8 and 10, 8 goes here. 9 and 10, 9 goes here. And then everything that's remained in this sub-array goes here. And then I move all of them back to the original array, right? You see that like we are using a temporary array here. So this is one of the disadvantages, or the main disadvantage of merge sort, that it's not in place. In order to merge 2 sorted sub-arrays, we're going to use a temporary array, right? Which is not always the size n. You see that sometimes it was size 2, now it's size 4. Next time it's going to be size 7. So this sub-array is now sorted. What we need to do is sort this sub-array. So again, what I do, 4 plus 6 divided by 2 is 5. So I divide this sub-array into 2. So I say that, okay, first sort this one, then sort this one, then merge them together. Okay, in order to sort this one, again, I'm going to divide it into 2. I'm going to sort this one, then merge them together. This is already sorted, this is already sorted, so now I can merge them. I compare 2 and 7, 2 is smaller, goes here, and then 7 comes here, and then everything goes back. Right, so now this sub-array is sorted. I have to sort this one. This is already sorted, right? Because it's only one element. So this sub-array is sorted, this sub-array is sorted, I have to merge them. I compare 1 and 2, 1 is smaller, goes here, and then like one array is now like everything has been one sub-array, everything inside it has been transferred to this temporary array. So like now I can just like move 2 and 7 over here, and then move them back here. Okay, so what we end up with now is like 2 sub-arrays that are sorted. This is sorted, this is sorted, right? Now what do I need to do? I need to merge them together. So I compare 1 and 6, 1 is smaller, goes here. 2 and 6, 2 is smaller, goes here. 6 and 7, 7 goes here. 7 and 8, 7 goes here, right? and then the rest of them, because this is empty, there's nothing to compare with, like everything is going to be transferred here, 8, 9, 10. And finally, these go back to the original array. So this is what merge sort is. Basically, if I want to write it, it's going to be like this. Say void merge. Let's say that we have an integer array and we want to sort it from index start and index end. So what we need to do, we have to find the midpoint. So let's say like integer mid is equal to start plus end divided by 2. It doesn't matter if the two sub-arrays have the same size. You saw that first time this had 4 elements, this had 3 elements. They don't have to have exactly the same size. So what we do here now, we're gonna call the same function. So we say that in order to sort this array from this index to this index, first sort, let me call this one sort, sorry. Sort the same array from the start index up to the midpoint, then sort the same array from mid plus 1 to the end, and then merge them. Let's say A, start and end. Okay, so we have 2 recursive calls. Of course, this is missing a base case, right? If we write the function like this, there is no like stopping criteria. So like it's gonna be stack overflow. It just like do this small, like it would be call this function infinite times until we run out of memory. So we basically make sure that if start is bigger than or equal index, return. If we get to a point that our starting point and ending point are the same, it means that we only have one element in the array. That's it, right? We need to stop. Otherwise, you have 2 recursive calls, and this is merging 2 sorted subarrays. The big O notation of merge sort is n times log n. I'm not going to mathematically prove this, but to give you an idea, like we are dividing the array into 2 subarrays. How many times can we do the division? Let's say like if we have n elements, we're going to make them 2, and then finally like we divide this until we get like 1 point. So how many steps do we have? We have log n in base 2 steps. And each time when we want to merge them together, right, the merging time, it's going to be in the order of n. So like this is not very accurate, but I just wanted to show you that like, okay, so we have these many divisions, and then at each step we also have to merge them. This is going to be order of n. So this is basically the big O notation of merge sort. The time complexity of it, it's going to be n times log n. We don't care about the base when we, or the coefficients when we talk about big O notation. That's why like we show it like this. One of the problems that we have with the merge sort is we need to have, like in the merging step, we need to have a temporary variable, right? A temporary variable. Sometimes it's size 2, sometimes it's size 4, sometimes it's size n, right? So we say that we need to have this much extra memory. It's not always n. Sometimes, most of the time, it's smaller than n. But the order of memory that we need extra memory that we need is order of n, right? And because of these copying into that temporary array and copying back into the array, we're going to lose some time as well. We say that merge sort is not in place. You saw that when I had to sort this, when I had to merge them, I moved them into a temporary array and then moved it back to the array, right? So that's one of the disadvantages of merge sort. Again, I want to repeat that the merge sort is comprised of two functions, one that's recursive, right? Once that recursive, that do the sorting, sorts the first half, sorts the second half. There is a stopping criteria. If we have only one element in the array, this is the stopping case. That's like how it stops. So if s gets equal to the end, that means that we only have one element left in the array, in the sub array. So that's it, like we don't need to divide anymore. And so like we basically sort the first sub array, then the second sub array, and this function would merge two sorted sub arrays. Okay, so this function, the assumption for this function is that we have an array that the first half from start to mid is sorted, and from mid plus 1 to end is also sorted, and this function would merge these two sub arrays into a sorted larger array. Okay, so that's what the merge sort is. In terms of time complexity is big O n log n, right? In the worst case, that's the like when the array is reversely sorted, it's gonna take a longer time. It's not an in-place sorting method because of this function, because when we want to merge two sorted sub array, we're going to use a temporary array. So we're going to copy the sub arrays into that temporary array. I just want to repeat that the temporary array is not always of size n. Most of the time it's a smaller than n, right? Because like let's say like when we had this sub array, you see that the temporary array would be size 4. When we had like this sub array, it would be size 2. Only when you get to the last step, it would be equal to size n. Okay, and so like it needs extra memory. So that's what the merge sort, it's a divide and conquer algorithm. It would just like divide the array into like half, tries to sort the first half and the second half, then merge them together. It's faster than it's more efficient than all the other algorithms that we've seen so far for most cases. Okay, so the next method that I'm gonna quickly mention, it's the quick sort. So as the name implies, it's a very time efficient algorithm. Most of the software packages that come with a sorting algorithm, this is the sorting algorithm that they implement. This is like quick sort. So let's say like Excel sheet, like when you want to sort a column or row, it's like usually they use quick sort algorithm, quick sort. Okay, so the quick sort algorithm, it's also divide and conquer algorithm. The first method, the first function that we have to know about is like you have to know about quick sort is partitioning. Okay, so let me make a just move these like so that like we have like, let's say this one goes here, this one goes here. Okay, so so the quick sort is basically has two like three steps actually, like partition and then sort and sort. So again, it's gonna call the same function, the quick sort function, recursively, right? But there is a second function that does the partitioning, which is what I'm gonna explain. There are different ways of implementing this one. So let's say that we have an array that's not sorted. We choose one of the elements of the array. Okay, so there are different methods to choose that element. You can choose the first element, the last element. You can choose randomly, or you can find the median point, the like number that's like the it's gonna be placed in the middle, right? So there are methods that do that. Like I'm gonna do a very simple method that I choose the last method as the pivot, what we call pivot. So what does this mean? It means that this is the number I choose as pivot, right? And what I want to do, I want to partition this array so that all the numbers smaller than 8 are going to be on the left side. All the numbers bigger than 8 are going to be on the right side, and 8 would be placed at the correct location. So this is how I want to divide this array into two sub-arrays. I want to have all the smaller numbers than the pivot, than the number I choose, on the left side. Numbers bigger than 8 on the right, or bigger than the pivot on the right side, and 8 at the correct location. So what I do, I start from here, like let's say like I chose this one as the pivot, the last element in the array. So what I do, I compare, I start from here, go all the way here, I compare this element with the pivot, right? If this is smaller than the pivot, like what I do, I have like a variable that I initialize it with -1 and like increment it, right? So like once I found this number, it's bigger, smaller than this, I increment this one, so this becomes 0, right? And then there is like also like there is no swapping needed for this case because this is the first number. But let's see. Now, then we get to this point. Is this smaller than that? No. Is this smaller than that? Yes, it is. So I'm going to increment this one. So I keep count of how many numbers are smaller than that. And I also swap these two. Okay. Then I look at this, 10, is it the smaller? No. 1, is it the smaller? Yes, it is. So what I do, I swap these two. Is 6 smaller? Yes, it is. So I swap these two. Okay, right? So now, like I forgot to like increment this. So this is like what we end up with. Actually, like you can start with 0 or you can start with -1. Then once you finish all the way up to the pivot, like you swap the pivot with AI plus 1, which is going to be this number. So now my array is divided into two sub-arrays. One is this one, the other one is this one. All the numbers smaller than 8 are on the left side, all the numbers larger than 8 are on the right side, and 8 is at the correct location. Now what I do, I repeat the same thing for these two sub-arrays. This sub-array and this array. So I choose this one as the pivot, right? Right, so like I compare 7, like it's not a smaller, 2 smaller, so I'm gonna swap. 1 smaller, I'm gonna swap. Okay, and then like what I need, like I eventually just gonna swap these two as well. So now again, this sub-array and this sub-array. Okay, so again, I'm gonna do the same thing here. This one would be moving here, and this one, just like there's one element, nothing here. So now this sub-array is sorted. Let's look at this one. I choose this one as the pivot, and eventually I have to swap these two. This become sorted. So most important part of this is the partitioning, right? Choosing an element of the array as the pivot. This one is an easy, like it should be an easy program for you to write. Okay, so that's why I don't want to spend too much time on it. You should have seen something similar to this in your previous courses. But what's happening in this, let me again like make this like a little bit unsorted. So like you choose an element as pivot, right? So it doesn't matter which element, well, like it does matter, sorry. But like in order to sort the array, it doesn't matter which element you choose as the pivot, right? Whatever you choose, it's gonna be eventually sorting the array, okay? In terms of time complexity, some pivots are better than the others. So if I choose this one as the pivot, like I want to make sure that all the elements smaller than 6 are on the left side, all the elements larger than 6 are on the right side, and 6 is in the right location. I compare 9 and 6, no. 2 and 6, yes. So I swap. 10 and 6, no. 8 and 6, no. 1 and 6, yes. Swap these two. 6 and 7, no. And I keep like counting how many elements are smaller than 6, so that like I know when I'm done where to insert 6. So now we have two sub arrays. I apply the same thing for these two sub arrays. So this is basically what's happening. Partition, then call the same function for the first sub array, call the same function for the second sub array. And this is eventually gonna sort our array. And the time complexity of quick sort is also n times log n for most cases. Like I'm gonna tell you like why I mean like most cases. It's an in-place algorithm. We don't need any temporary memory. Now, like in the worst case scenario, so like before I talk about the worst case scenario, as I mentioned, you can choose the last element as the pivot. You can choose the first element as the pivot. You can choose any random number, random element as the pivot. Or you can write a function to find the median number, right? So like here, the median number, it's gonna be, I think 7. That's gonna be the, like if I, like 1, 2, 6, yes, 7 is gonna be in the middle. If I, like in the sorted number, like which one is gonna be in the middle. So there are like different methods to choose the pivot. Either choose the first one, last one, randomly. Like what I mean randomly, you just write a function that like that I is equal to, let's say rand mod, so in this case 7, right? And then like eventually, like when your starting index gets bigger than 0, then you have to do some manipulation here. But you can choose your pivot either as the first element, last element, random element, or you can choose it, you can find the median number and choose your pivot as the median. In the worst case scenario, which is this case, when the array is reversely sorted, 7, 6, 2, 1. If you choose the last element or the first element as the pivot, this is going to cause a lot of problem, right? So this is basically what's going to happen. in this case, like the choice for pivot is going to be very important. In this case, if you choose like first or last, basically your big O notation becomes n squared. Okay, so so that's why like in most implementation of quicksort, they either choose pivot randomly, or like depending on the application, you can choose the median. Like it's gonna take some time to find the median, but overall, if you're dealing with large numbers, it's gonna be more efficient to either choose these two as the pivot. For this course, like I'm not gonna focus that much on the choice, but I want you to understand like why this is gonna cause problem in some cases. Okay, so in this case, like let's say that I choose this one as the pivot. Okay, it's not smaller, it's not a 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 smaller. Okay, so this is gonna be moving here. What happened now? This part, the whole array is like my sub array. So you see this, like the whole point of quicksort was divide and conquer, right? We wanted to make the sizes smaller. We wanted to divide the size into two, ideally. But like once you have this case, if you choose this one as the pivot, then like the size doesn't change that much. It's like gonna be reduced only by one. Okay, so this is not what we wanna have, right? This is not what we wanna have, right? So that's why, like I said, like in the case that your array is reversely ordered, if you choose the last element as the pivot, this is actually gonna be big O notation n squared. So in most implementation, like either you want to choose it randomly to mix it up, or you can find the median. If you find the median, then like you're sure that, okay, this element is going to be at its correct location, it's right, and then like you make sure that you always divide the array into two halves which almost have the same size. It's either like exactly the same size, or one is one larger than the other. Okay, so that's basically what quicksort is. We're gonna see the implementation of it in the lecture. Thank you so much.